Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to finite element methods. In the last class we have learned about constitutive relations. Let us extend that little bit further and let us dig the relations of the isotropic case further. This is the relation we have looked at in the last class in the tensorial form. That is sigma ij is nothing but 2 mu epsilon ij plus lambda delta ij epsilon kk, where I have mentioned this mu and lambda are called the Lambis constants, and this sigma ij represents the stress tensor and epsilon ij represents the strain tensor, delta ij represents the Kronecker delta, and epsilon kk represents the trace of the strain tensor, that is epsilon 11 plus epsilon 22 plus epsilon 33. Now the property of delta ij, I have mentioned it again, which is nothing but the Kronecker delta, that is given as delta ij is equal to 1 if I equal to j, equal to 0 if I not equal to j. This is for your reminder. So now if you throw some values of I and j here, where I runs from 1 to 3 and j runs from 1 to 3. So if I throw I and j as 1 1, so this is sigma 1 1 equal to 2 mu epsilon 1 1 plus lambda delta 1 1 epsilon kk. So that can be given as 2 mu epsilon 1 1 plus lambda delta 1 1 epsilon kk, that is equal to 2 mu epsilon 1 1 plus lambda into, since delta 1 1 is 1, I have removed that, that is lambda into epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. Similarly, I can write the normal strain in the y direction, in the second direction, sigma 2 2 as 2 mu epsilon 2 2 plus lambda into, again this I and j will be 2 and 2, since I equal to j, that will be 1, so it will be lambda times again epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. Similarly, sigma 3 3. These are the normal components. Now if I throw I and j as different, that is if it is sigma 1 2, then here it will be delta 1 2, so I not equal to j, so this term will vanish, this entire term will vanish, and the only surviving term will be the first term, that is sigma 1 2 is nothing but 2 mu epsilon 1 2, and sigma 2 3 as 2 mu epsilon 2 3, and sigma 1 3 as 2 mu epsilon 1 3. So lambda and mu are called the Lambis constants, and they can be given as lambda is equal to e mu by 1 plus mu into 1 minus 2 mu, and mu is nothing but e by 2 into 1 plus mu. So if you remember this form, mu is nothing but the shear modulus, that is our famous relation, if you remember, E equal to 2g into 1 plus mu in ug, where we usually represent the rigidity modulus with g, but here that will be mu. So g and mu both are same. There is a rigidity modulus which relates the shear stress with the shear strain. Now this lambda is called the Lambis constant, both are Lambis constants, where it is related with Young's modulus, and this is nu, not mu. This nu represents the Poisson's ratio. So nu will never be 0.5. If you see from this relation, if nu is equal to 0.5, this lambda will tend to infinite, which is meaningless. So that is why nu will never be 0.5, that we already know. The other definition we can introduce here is the bulk modulus. So bulk modulus is the ratio of the hydrostatic pressure to the fractional change in volume. That is, it is represented with k equal to minus p by change in the volume, fraction of the change in the volume. That is, delta v is the change in the volume by the virginal volume, that will represent the ratio of the change in volume by virginal volume. So now if you take the ratio of this hydrostatic pressure by this one, and we have kept the negative sign here because this hydrostatic pressure itself is a negative quantity. In order to negate that, we have kept the negative sign here. So that is why I have represented this p here as p equal to minus sigma ii by 3, where this I is the repeated index. So this can be represented as minus sigma 1 1 plus sigma 2 2 plus sigma 3 3 by 3. So if you remember this is the hydrostatic part of the any tensor. So any tensor, if you remember hydrostatic part and deviatory part of the stress tensor, while calculating the hydrostatic part, what we have written is sigma h is nothing but sigma 0 0 0 sigma 0 0 0 sigma. This is the hydrostatic part of sigma, where this sigma is written as sigma 1 1 plus sigma 2 2 plus sigma 3 3 by 3. This is nothing but the trace divided by 3, that is we took the average. We took the average of the normal components. So now this is nothing but the hydrostatic pressure. So the same thing we are using here. So this is the hydrostatic component. This is P equal to minus of sigma 1 plus sigma 2 plus sigma 3 by 3. So the ratio of this P with respect to the fractional change in volume will give us the bulk modulus. So now here P is a part of hydrostatic component of the tensor sigma. So now while coming to the solution part, so we have introduced so many things, so many definitions until now. So now what are we going to do with these definitions? What are we going to do with these strain displacement relations, with the constitutive relations? What are we going to do with these things? We are going to solve the real problems. So how do we solve them? Any solution for elasticity problem, let us say we are solving the elasticity problems for small deformations. So that is very, very small. Elasticity problems, assuming linear elasticity, must satisfy the following. So if we want to solve some elasticity problems, then these are the requirements. So what are the requirements we are having? The first requirement is the stresses must satisfy the equilibrium. So we already know what is the equilibrium equation. So what is the equilibrium equation? Sigma ij comma j is equal to 0. This comma is called the differentiation operator. So we are having three consecutive equations here. So any structure has to satisfy this equilibrium condition. That is the first prerequisite in order to solve the problem. The second thing is the corresponding strains must be the derivatives of the displacements and satisfy the compatibility equations. There is something called compatibility equations in which I didn't cover. So the compatibility equation says that there are some six set of equations where they can be comprised of curl epsilon equal to 0. So we will get some 6 equations. These are the compatibility equations. This says that, so since we are having 3 displacements basically, if 3 displacements are given, we can calculate 6 strains. We are having 6 independent strains, 3 normal strains, 3 shear strains. But they are given 3 displacement maps. Now, what if I have given the strains and if I want to calculate the displacements? Because we are having surplus equations, but the number of unknowns are only 3. So for this sort of problems, we need to have the strain compatibility. That is, we will be having some set of equations where it must satisfy. Otherwise, there will be an overlap of the material or there will be voids in which that must not happen. So that is why strain compatibility is also important. So now, the corresponding strains must be the derivatives. So whatever the displacement maps we get, those displacement maps we must be able to differentiate those maps to get the strains. So that must be there. And the third one is the elastic strains and stresses must be linearly coupled with suitable elastic constants. So we have seen the different elastic constants, that is, we can have anisotropic and isotropic elastic constants. In the case of isotropic elastic constants, we'll be having only 2. For the case of anisotropic, depending on the crystal symmetry, we will be having varying independent constants. In the case of triclinic, it is 21. In the case of cubic, it is 3. In the case of transversely isotropic, it will be 9. Like that, we will be having different independent constants depending on the material symmetry. So that also we need to be careful. Based on this, how can we solve these things? The solution methodology. We have our constitutive equations, strain displacement relations on our hand. We know the constitutive equations, that is the relation between the stresses and strains with some preferred elastic constants. And the strain displacement relations, we are having that epsilon x is equal to dou u x by dou x, epsilon y is dou u y by dou epsilon z is dou u z by dou z. Like that, the normal strains and the shear strains, we are having all these relations. Now, the equations can be framed in terms of the displacements as, now I want my primary variable as a displacement. I want to calculate the displacement first for a given respective loading. So for that, now I am framing some equation here. So how do I framing that one? First, I took some constitutive equation. I took the constitutive equation, that is sigma ij is equal to c ij k epsilon kl. Where this epsilon kl is nothing but the symmetric part of the displacement gradient. So I have written that one here. So u k comma l plus u l comma k by 2, that represents the symmetric part of epsilon kl. Now if you multiply the c ij kl with these components independently, where these components will turn out to be same, because c ij kl is symmetric with k and l as well. That is, if I change l with k and k with l, that doesn't matter. My c will remain as it is. So that is why these two terms will be the same. So that is why this sigma ij will boil down to sigma ij is equal to c ij kl dou uk by dou xl, where this dou uk is a field, is a displacement field, which is a function of the reference configuration. That is, this displacement field is a function of reference coordinates. That is, it will be having x1, x2, x3 as the coordinates. So this is the relation we are having. Now, substituting sigma ij in the equilibrium equation, we are having stress here. Now that has to satisfy the equilibrium equation. That is our first prerequisite that we mentioned. Now sigma ij comma j is equal to 0. That is, if you differentiate this expression with respect to j, now this will be changed to Cijkl dou square uk by dou xl dou xj, that equal to 0. So this is our governing equation. It's a second order equation, second order PDE, where we need to calculate the displacements here. And if you see this, how many free indices we are having here? Here k is repeated, l is repeated, j is repeated. We are having only one free index, that is I. So I runs from 1 to 3. So this will be having 3 equations where we are having 3 unknowns. What are the 3 unknowns? We will be having 3 displacements, u1, u2 and u3. So the unknown is the displacement field uk. That is the displacement field we want to find out. So from this expression, find the displacement first. If you get the displacement, then differentiate the displacement field, then you will get the strain. If you get the strain, then calculate stresses from the constitutive equations. So we will get the displacement from the governing equations and differentiate uk with respect to the coordinates for strains. Now use the constitutive relation to get stresses. So this is one of the solution methodologies. This is one of the way to solve this. We are having multiple ways to solve this one. We can introduce some eddy stress function, nothing but phi, some scalar function, and we can solve this one instead of solving 3 equations like that. We can do multiple things to solve these equations, to solve these expressions. And one more thing, I have missed the body force here. I have simply written sigma ij comma j is equal to 0. So one can write the body force terms also. That is sigma ij comma j plus fi equal to 0. This is how we see the equilibrium equation. That is, these are the external forces because of these stresses are happening where there is equilibrium. This is the equilibrium condition. So this fi can be included here while writing these expressions, while writing these equilibrium equations. Thank you so much for watching this video. Stay tuned to Ekeeda, subscribe to Ekeeda.